50 volts peak. Second thing was it was a source resistance of 100 ohms, right? Third thing was the Z antenna. And Z antenna was 72.3 plus J 42.5 ohms. All right, it's a half-wave dipole. If you were to draw this, it would look like this. And here's your antenna. It's an exact lambda over 2 dipole. Here's theta, there's R. And you come out here some distance and they want E. And they want H. And P average here. And they want the total power radiated by the antenna system. Well, you can get this several ways, by the way. P radiated, they wanted the length of the antenna. And I think that's about it, right? So if we look at this circuit, the equivalent electrical circuit to get the current is just this. It's a voltage right here of 50 volts peak. Have RS here of 100 ohms, right? And then you have the antenna, which is 70.3 plus J 42.5 ohms. And I wanted to get this current. By the way, I'll put the solutions up. So this current's magnitude is just going to be the magnitude of 50 over 100 plus 72.3 plus J 42.5. So the only thing you care about is the magnitude of the current. Once you have the magnitude of the current, I put the formulas on the board for the actual E field. By the way, people made equations with that angle. They made, mistakes when they took the cosine of 60 degrees times pi over 2 and then got a cosine. And I think it was degrees radians problems. If you're having trouble with that, put all your angles in terms of radians, because there's a pi over 2 that are radians after that cosine. Let me just put this up. The E field itself from a half-wave dipole, oriented on the z-axis, is J, then it's 60 over R, then it's times I naught. So length isn't in this equation. E to the minus J beta R, and then it's times the cosine of pi over 2 cosine of theta over the sine of theta. And it's in the A theta direction. I gotta make mention of one thing here. You see this angular function here, the cosine pi over 2 cosine theta over sine theta? Everybody? Its peak value is 1. When I see values of that evaluated, they're 1.5 or 1.3 or 1.1, I know you've messed up in a big way somewhere. I don't know where sometimes, because I just see a formula that I wrote on the board, and then I see an answer, and I can't figure out what you did, because it's in your calculator. But this thing can never be greater than 1, the angular function. You got that, everyone? Don't make this mistake again. So this is never greater than 1. The I naught is really that I right there. By the way, can you tell me what that value is? I don't have my, right off your paper, just give me I.
Oh.
Magnitude.
0.28 amps.
Yeah, that's right. 28 amperes?
Yes, sir.
All right, and that's just, it's the magnitude you care about. Y'all follow, you don't, yeah.
I have a question before you get too far ahead on the angular argument there.
Yeah.
So in the future, theta needs to be converted to radians.
Well, let me put it to you this way. You don't have to, but see this pi over 2?
Is there?
That's radians times cosine of something. All right, if you're gonna do degrees, then this is 90. Y'all see what I'm talking about? It's much better to put pi over 2 and put the angle in radians. I mean, I'm speaking from experience.
So that's your recommendation that anytime you see.
I don't like messing around with radians and degrees in the same problem. I prefer to default to radians because I know this is in radians already in the standard form. That's just me personally, but I try to make my life as simple as possible when it comes to engineering problems. You'll make enough mistakes, all right, without making the problem complex. I guarantee that. And if you're worried about your grade, there's probably going to be some adjustments. I'm just trying to encourage you to don't do stupid things. Like, this is not a hard quiz. This was meant to be a checkbox quiz. Just run through it. There are only a few really high scores. All right, back to that. That's that. So y'all see we can literally stick in theta, which was given as 60 degrees, and r, which was given as 200 meters, right? And now it's turning the crank. Do y'all agree with this? And I'll just tell you this, you don't even need to consider this phase term there or there, because the only thing I care about is magnitude. Y'all follow me in that class? On exams and quizzes, unless it's specified, and I really would underscore it, only thing I care about is magnitude. So here, when you go about doing this, I wish I could get this from memory. Believe it or not, I mean, everybody had the formula down, it was on the board, right? Some people had the right value of I, and they got the wrong value of the E field. And that troubles me personally, because it's telling me, in the clearest possible way, they don't know how to evaluate this in the calculus. So remember what I just said, all right, about making sure, if you're gonna work in radians, work everything in radians. If you're gonna work in degrees, this has to be 90, not pi over 2. Y'all follow me? Can you all see? Can you see back there? Please don't make that mistake. I work in radians because the general default for like beta is radians per meter. Beta is radians per meter, so it's easier that way for me. All right, back to this. What did you get for the magnitude of the E field? I forgot what it is actually.
68.7 millivolts.
That's it. 68.7 millivolts per meter. All right, now that's E. Now a lot of people, and you got credit for this, a lot of people just said, even if this was wrong, if you said H is just equal to magnitude of E over eta, you're going to get a point for that, just having that down. Even if you had E wrong, but that's how you get it, right? Can you see it in the back? I mean, this is just the standard form, and for this one, eta is equal to 120 pi, because it's in bare ohms. Can you give me this one? I forgot.
182.2 microamps per meter.
Microamps per meter. A lot of people messed up the units. For E, that's in volts per meter. I saw amps per meter for E. I didn't know how they were getting that. And some people just put down the wrong answer, the wrong space. I give you credit if it was right in your formulas and you just copied it wrong. All right, that's H. Then after this was the average power, PF. Now there's several ways to do this. One way, and the way I like, is just 1/2 the magnitude of the E field squared over eta, right? That's one way, and we know that for any propagating wave, that will be true. Correct, everyone? No question about that. I think I wrote this on the board too. It's also what? 15 over pi times I naught squared over r squared. And then it's going to be times that angular function squared, right? Cosine of pi over 2 cosine of theta over the sine of theta squared. They will give you the same answer when you do it. Either one. So you can get at this from two different ways. And some people, and I'll put this on the solutions, you'll see this. You can do either of these, it'll give you the same result if the E field was right the first part. If not, this will give you the right results, assuming I is right and your angular function is evaluated correctly. Can you give me that?
6.26 microwatts per meter squared.
6.26
Yes, sir.
microwatts per meter squared. Okay. So that's PAB. Let's see what else. The radiated field. Now, you didn't have to integrate anything, right? I gave you the antenna impedance. Y'all follow me on this, please? Listen to this part. Here's where some people drop the ball. You had it right up to this part. All right. The radiated power from this antenna, if I know the current, is 1/2. Now it's magnitude of the current squared. That's the feed current right here. And then it's times the antenna impedance that's real, the real part of it, or the radiation resistance. And I have a comment here. I didn't look at everybody's paper carefully on this. This cannot have an imaginary part. If there's a plus J something, you messed up in a big way. The magnitude of I there gets rid of the J. Now what some people have done is they got I and it had a real and imaginary part. Hear me on this, right? And what they did is literally took I and multiplied it by itself. So they had an imaginary part. Y'all hear me? That is wrong. It's the magnitude of I that goes here and you square it. All right, and please make a note. If you made that mistake, write it down, don't do this. Because it's real important that you understand when something has to be strict real. And power, radiated power is strict real. All right? That's radiated power. I think the next thing is the length of the antenna, correct, class? Now, these are sort of things, I'm trying to just give you some points here, honestly. So the first thing you have to do, the frequency I gave you is a gigahertz, or 10 to the 9th hertz. Giga is 10 to the 9th. And we know wavelength in free space is C over F, right? So it's 3 times 10 to the 8th meters per second over 10 to the 9th, and that's cycles per second. And that means it's 0.3 meters or 30 centimeters is a full wavelength. Correct, class? The dipole is a half wavelength dipole. It means it's half that. So L here is just lambda over 2, or it's 0.15 meters or 15 centimeters, or however you want to put it. Do y'all follow me? Now, if you look at that homework assignment, you're going to see this problem literally is stated explicitly in there. All right? Yes. Bless you.
So for the E field, can you like write down what values you put in to get that 68.7, or how? Because I'm not getting that.
I naught is right here.
Yeah.
All right. Theta is 60 degrees, or if you're using radians, theta would be equal to pi over 3 radians. Okay? All right, and if you plug it in, it'll come out right. It'll come out to this. The reason I know that is because I checked that carefully. I saw so many people that didn't get that. It was starting to concern me if I got it wrong, but I ran it. It's right. Okay, class? Please make sure most of the time, this is my opinion now, most of the time it was either the current value or the evaluation of this. And more, I'd say it's about a 50-50 split. A lot of people, even if they got the current right, they had trouble right here. And I don't know what to tell you. Because that was part of the homework. I gave you several problems with this, literally, where you had to apply all this stuff you learned here to solve it, or that I'm quizzing you on here. All right? Now, yeah? Do you have a question?
What's the value, what's the answer for PRAD?
Oh. I think it's 2.8 watts. Is that right? You check me on that. Then the only thing you need to do here is, here, I'll just tell you, the exact thing for PRAD. That was 1/2 magnitude of 0.28 squared, and it's times 72.3 ohms, and that should give you the value of 2.8 watts. Okay? You go ahead and check me on that one. All right, now, we went over monopoles last time, right? I gave you, there's several problems I just asked, not a whole bunch, there's like 3 or 4 problems I asked you to do with monopoles. Did anybody, first, how many did them? If you're level with me, we can move on, we can get through this. 1, most people didn't do the monopole problem. The monopole ones will come back at you, and I'm gonna tell you this much. It's best to make sure you know how to do them now. You might as well do one of them, simply because the real truth of this is with the monopole, it's so easy, people will make mistakes. That makes sense. It's so easy, people just overlook stuff and they make mistakes. Bless you.
Thank you.
I think it's ragweed if you have allergies, but I don't know what else is in force right now, but there's a whole lot of people suffering from allergies around here. Sneezing, drippy eyes, inflammation, stuff like that. guess I am too for a little bit. So for monopoles, let's do a problem. I prefer one out. Do you have the homework in front of you? Hang on. Anybody have that homework from? Can you
I
give me
can.
the first monopole let me look. Thank you.
Mhm.
It's just
No, it's not.
slow down. Right here. Quarter wave monopole. Give me, this is gonna be 7.2.2, is that right?
Yeah.
Go ahead and give me the, it has a value of voltage source of
100.
RMS?
Where does it say? It doesn't say. A quarter wave monopole antenna is situated above a perfectly. Okay.
100 volt, okay, so that's peak. If they don't say RMS, assume peak.
300 millihertz.
So this is peak. F is 300 megahertz.
Yeah.
300 megahertz. What else?
An impedance of 50 ohms.
For the monopole?
Yeah. That it has a source impedance of 50 ohms.
Uh-oh. Hold on. Source impedance, RS of 50 ohms. Go ahead.
Determine the average power radiated. Also determine the magnitude.
Oh, what length monopole? Quarter wave?
Yeah, quarter wave.
All right, so L is a quarter wave long monopole. And did it give you an antenna impedance? Did it say 50 for that?
That's the source impedance of
Wait,
50.
is there an impedance for that antenna?
No.
All right, class, listen carefully to this. This is a monopole. Remember, a monopole is just like a dipole, except the directivity doubles and the impedance is half. You all remember that, class? That means the impedance itself, Z antenna, unless they say, or I say that it's cut down to 0.485 lambda for half wave, or half of that for quarter, then you don't have an imaginary part. You have to assume it's going to be 73.2 plus J 46.5 divided by 2. Y'all hear me? It's the same impedance that a half-wave dipole would have, only half. Everybody with me on that, class? So what is that, 36? What is it? 36 points
36.6.
plus J 20.
23.25.
And that's right, about right. Okay? So we're gonna get this, and here's what I'm gonna do. I'll draw the circuit. I'll just show you the antenna. It looks like this. Here's the ground plane, and here's your monopole. This is a quarter wave monopole. I know the impedance, the driving point impedance right there. What I really need to get is the current, right? Because if I get that current, I know that the E field will be the same as the E field from a half-wave dipole. A full half-wave dipole would just be J60I over R, e to the minus J beta R, then times the cosine of pi over 2 cosine of theta over the sine of theta in the A theta direction, unless otherwise specified. That's what it will be. Also, well, there's a couple ways to get it. Yeah.
Instead of 46.5, should it be 42?
42.5, you're absolutely right. 42.5, my bad, and that makes this
20. No. 21. $21.25.
Yeah. That won't have that much of an effect. Anyway, when we do this, the circuit for this would look like just the voltage source right here. Then you put the source resistance in, whatever it is, and then the antenna impedance right here, and you get the current I. So that current I, of course, is Vs over RS plus Z antenna. And We just need the magnitude of it. Anybody got a calculator and can do this for me? So RS is gonna be 50 plus 36, so it's 86.6 plus J, 21.25 divided into 100. And just give me that current, if you don't mind. I wanna go through this problem with you, because a lot of people have problems on my quiz and it concerns me.
Zero point eight nine one, or 92.
0.892.
Yes, sir.
Anybody else confirm that?
It was the,
Say again?
yeah, someone else needs to check that, because when you were yelling out what to do, I just was like halfway listening.
I'm checking it.
It's just 100 over 86.8 plus J 21. It looks right.
It's the conjugate, actually,
Well, I don't care, I just need magnitude.
so I think it's.
Yep, you got it?
I got 0.767.
Say that again?
0.767.
Anybody else?
I got 1.9.
I got
It can't be
1.12.
one, because
Okay.
look,
Gosh.
you got
Oh,
100.
shit.
Well, maybe it could be, actually.
1.12.
I take it back. What did you get?
It should be 1.12, I think.
That's what I got, 1.12.
All right. Anybody else?
Would you like
What
to?
I'm really telling you is, you're gonna make mistakes like this and lose a lot of points. So the moral is, don't make mistakes. Be attentive to detail, honestly. It'll save you a lot of anguish. A lot of people just, they're thinking beyond this. They're not focused on getting this right. Y'all agree with this class, Amps?
So what's the correct method of doing that then if I'm getting the wrong answer?
Well, I don't know what you're doing, but generally just put VS as 100. The equation is I is equal to the magnitude of 100 divided by, and it would be 50 plus this side would be 86.6 plus J, 21.25. Now, if you really wanted to, get it down to the nuts and bolts, square that, and take the square root to get a magnitude at the bottom and just divide that into 100. But it shouldn't be a big deal. You should be able to get this fairly quick. Y'all got it? All right, we got that. What angle was it at?
Of course.
Didn't get it?
90 degrees.
90 degrees?
90 degrees.
You know what makes 90 degrees so attractive? Anybody? Why do I like 90? Just one look at that. This angular function is 1 at 90, same as the sine, okay? That's the nice thing. If it's at 90 degrees, the angular function is 1, so I'm going to just erase it. All right? The other thing, did they ask for a phase for that E field? I'm going to tell you this, I don't ask for phase when I talk about E field. It makes no sense to do that in the real world. You don't have anything to use as a phase lock loop or something to compare it to. What'd you get?
It doesn't ask.
Oh, fantastic. That means I can get rid of this too, right? Y'all with me on that? If it's at 90 degrees, the angular function goes away. It's only magnitude, the e to the minus j beta r and the j in front of it we erase too. Y'all follow me? Since that's all phase, right? Now what is this gonna be? Get rid of that j. Well, 60 times I, 1.12. And what's the distance r?
100 meters.
Oh man, this is nice, I like this. So, that's basically 0.6162 maybe? What are you getting, 0.601? 60 times 1.12.
0.672. 673.
Volts per meter, right?
Yes.
What's the answer in there?
Where
At the
would
bottom?
0.674 volts
Well,
per
we're
meter.
missing there. Kidding. Y'all with me? So we checked that box. Now, what else does he want? H?
No, the total average power radiated
Yeah, we'll get that in a second.
and the magnitude of the electric field.
You got the magnitude.
Yes. And then the direction of the electric field vector with respect to the ground plane.
It's perpendicular to the ground plane. Let me explain that. The E field, the antenna is pointing upward in its E direction. Ground plane is in the XY plane. All right. The E field, if you come off any radial distance, the E field is always perpendicular to that radial distance, and it has a component in the vertical axis, no component in the horizontal plane. When it's directly on the surface at theta equal 90, it's vertical, it's just in the Z direction of perpendicular, whatever it says, all right? So that's the orientation. That's the magnitude right there
Power density
at that point.
at 100 meters.
How do we get power density, class? If we got the E field, how do you get it, anybody?
192 squared over 2 eta.
Yeah. For average power density at that point, it's just gonna be 1/2 magnitude of the E field squared divided by what? Eta, and eta is really, eta naught is 120 pi ohms if it's in air, it's in the AR direction. Can you do that for me? Because that's just taking that value, squaring, divided by 2 eta naught. Make sure you get the right answers. It always concerns me when you think you know what you're doing, but you're getting the wrong answers on your calculator. It tells me that there's something amiss with your understanding of your calculator. You got it, 36x. What kind do you have? TI what? An 84 plus? Are you getting these answers? You got Inspire back there? You got Inspire? You got the same, I mean, give me this answer right here.
6.6 times 10 to the negative 3. So
0.6 times 10 to the minus 3, and that would be watts per meter squared. You guys getting that? 6 times 10 to the minus 4? Y'all getting it? Okay, good. So that's the average power. How do we calculate the radiated power now? Anyone? Anyway, radiated power.
The 1/2 I squared R radiated.
Yeah, P radiated, if you've got the current, just go for it's 1/2 the magnitude of the current squared times the radiation resistance, right? The mistake that's likely to happen there is you're going to use 73 or 72.3, just because it's sort of a knee-jerk reaction. It's not that, is it? It's half that, right? You with me? It's exactly half that. That means P rad is really 1/2 right here. Then it's times the magnitude of I, which is what, 1.12 squared, and our radiation is really 72.3 over 2. And I'm putting it there for a reason, so you'll understand where I got that. I took the half-wave dipole's radiation resistance and I divided it by 2. Got me, class? What do you get for this? For P rad? Say that again.
23.
23 watts? Is that what you got? 23 watts. All right? Y'all follow me? I'm going to show you something else to do in a second. Is everybody with me on this? All right. Now, just consider what I showed you. I'm going to show you a different approach to get the same answer. It's a little easier a lot of times. All right? I'm going to do it right here. I'll leave the current value right there, but, all right. Another way to do these kind of problems is, you all agree we can find the current from understanding Z antenna, RS, and the voltage, right? The open circuit voltage, right? So if you have current, and we do, the next thing you get if you want to do the problem, this is a little quicker, believe it or not, usually, is to find, and we do have the radiation resistance. So we have I, we have R radiation resistance, which is 73.2 divided by 2. And that's, what, 36.5 roughly ohms, right? Now we find the total power radiated. That's 1/2 magnitude of I squared times R rad. All right, we'll get that, and we have that down there at 23 watts. Now, to find the power, you get the power density next. I know the average power density will be equal to total power radiated divided by 4 pi r squared. That's the isotropic power density would be there if there was no antenna. It was flowing out the same amount in all directions. Y'all follow me on that, class? If there was no antenna, it was just going out in space without any kind of focusing, that's what you get. Then you multiply it by the directivity. Now, the directivity for a monopole is twice that of the equivalent dipole it could be drawn from. You all with me? So it's going to be 2 times 1.64 because the value of the magnitude of the directivity for a half-wave dipole is 1.64. You all with me on that, class? Then it would be times that angular function. I'm just putting it in here so we don't omit it. All right? And that will, yes, sir.
I have a quick question about the first one. Like, why we use R rate as 70.2 instead of?
What's the radiation resistance for a half-wave dipole? Do you remember? How many know? Oh, 72.3. Sorry. 72.3. I haven't transposed. It's about, what?
It's 70.2.
Pardon?
It's 70.2. You were right.
Oh,
Yeah.
73. You know, the funny thing is, you're going to look online. I'm just going to tell you this. If you look online, you're going to see this represented as 72 ohms, as 73.2, and as 72.5. And the reason is this. The thickness of that wire is critical in that value. It's around 72 to 73 ohms. It's not exactly that. Y'all follow me? In Whitworth's book, it is 73.2, but in my other book, it's 72.5, I think. Yes, miss?
I'm just saying,
Yeah.
why don't we plus that 42.5 J?
Say again?
Like, cause we have our, oh, that's the thing. Oh, never mind.
This is the it's just the real part of the radiation resistance of the monopole. You forget the imaginary when you calculate radiated power. You take this, and then this is the equation I really want to talk about, because now this gives me, I don't go for the E field, what I do is go for this first of all. Got me on that? Now this angular function is 1 if theta is 90, right? We're going to do the same problem. If it's 1, then we forget about it. And this is going to give me the same radiation or same average power density as that did. You can check this. Well, it's got to, frankly, if we've done it right. So this is 0.6. If somebody wants to check me, it'd be great. I'll just put it as 6 times 10 to the minus 4 watts per meter squared. This is the progression. This is the way I usually do it in radar, in my EMC course, and all that. That's the average power density. You follow me? It's at the point theta equals 90 degrees. R was 200. Is that right? What was R? 100?
Yeah.
100? So, I have that. Then I use this to get the electric field. Now, this is the way I do it. I take that, this average power density, and I get the electric field. I say now the electric field magnitude. Well, I know this. I know 1/2 divided by eta times E squared is equal to P Av. And therefore, the E field magnitude is just equal to the square root of 2 eta times P Av. Y'all follow me? Because usually what's given in these things is the antenna impedance, the real and imaginary part, and the directivity as a function of angle, so you can get at the power density easily. Now that's the E field magnitude. It'll be the same as we calculated, about, which is 0.673 volts per meter. And then you can get the H field just dividing that by eta, right? Now, I'm just showing you this to be sure you understand that with a monopole or a dipole, a monopole is just like a dipole. It's just directivity doubles, radiation, or really the antenna impedance is halved for an equivalent full-length dipole. For a monopole, which is half as long, the impedance is halved, directivity is doubled. Y'all follow me in that class? And that's really it in a nutshell for monopoles. There's no other tricks, okay? Now that's monopoles that are vertically oriented. If you ask me what happens if you make them parallel, there's more to that story that we cover. We don't cover it in this class. You get it in antennas or EMC. But really what happens then, you have to do the imaging method with parallel currents, and it's more involved. Okay. Now, are there any questions about the homework about monopoles in general? All right. So next, in Dr. Whitmer's book, I'm going to follow his progression. I'm going to do arrays. Then I'll show you the complete, really Friese equation and exact nature of the antennas. Actually, since I have 10 minutes, the arrays will take a little longer. What I'll do is, actually what I'm going to do is the Friese equation. I'll do this next, then I'll do arrays next class. So F1 Friese equation. Write this down. And this is important because this is how much power you can extract from an electromagnetic field that's propagating from an antenna. Now, let me show you the way this works. If you have an antenna down here, and this is going to be my transmitting antenna, and it's got a certain amount of radiated power, and I come out a distance r away at some angle theta. Now what I'm trying to do is just show you what you've been seeing over and over again. Only now I'm giving you the total radiated power. I'm telling you how far away you are, r. And I'm going to say something here. The gain of this transmitting antenna will be the directivity of the transmitting antenna as well. Or I can say the efficiency is 100%, or really the efficiency is 1. Now, I'm doing that for a reason. You got me? Please follow me on this. Yeah.
No, sorry, I'm stretching.
I mean, everybody with me on this so far? All right. That means if that's the case, if I know the gain, I know the power radiated, know the angle, know R, I know that P rad here, or I'm sorry, average power, pardon me, is equal to the radiated power, and I do this all the time this way, over 4 pi r squared. That gives me the isotropic power density as if there was no focusing, and then I multiply by the directivity or gain. And then I take times the gain of the antenna, the transmitting antenna. And this will be a function of theta, possibly theta NP. And that's the average power density out there. Y'all with me? Now a good question is, well, what if I have an antenna out here, and this antenna is going to have a gain of the receiver. This will be the receiving antenna. And what I want to know is how much power is received. So that's my goal. Now here's how we get that. And this is important you pay attention. Y'all follow me? You got power coming into it. We know the power density. Well, how much power is actually received by that antenna? And here, Dr. Whitmer's book does not prove this. It's a proof that is kind of based on something called reciprocity. Now here's the deal. You know how if you have an antenna that transmits, the directivity basically tells you how much power is in a certain direction, right? It basically tells you how the power is distributed. But that directivity or gain really gives you something else. It's the electrical area, the equivalent area. It's called aperture of the antenna. Now, the aperture of the antenna is in meters squared. This is usually the way it's shown. It's either a sub p or a sub b. And it's equal to lambda squared over 4 pi times the gain of the antenna. I have to just tell you, you're still wondering why, big deal. All right, aperture is an area, it's in meters squared. Power density is in watts per meter squared. So to get the power received at that antenna, it's really the aperture of the antenna, the electrical size, times the average power density of the incoming wave. It should make intuitive sense to you. If you know what the power density is striking an antenna, if you can find some measure of the electrical size in meters squared, you should be able to use those two things to get that. And that's exactly what it is. So really, the power received is equal to lambda squared over 4 pi times the gain of the receiving antenna. That's the area. It's that times the average power density striking the antenna. Well, what's the average power density striking the antenna? It's the radiated power over 4 pi r squared. It's times the gain of the transmitter. Just take a look at what I've written. You agree with that? The first part is the area, the size in meters squared. The second part is how much power, what the power density is striking it. Now, usually with the Friis equation, they do this. They want the ratio of P received to P radiated or transmitted. Dr. Whitler's book is going to have something like P received over P transmitted. Radiated, transmitted is the same thing. It's how much power is launched from the actual antenna that's sending the signal. And the ratio of those things, kind of interesting when you look at it, you're going to have lambda over 4 pi r, and that mess is squared, and then it's times gain of transmitter, gain of receiver. Can y'all see that? This is the Friis equation, right there. Now, something to take note of is that lambda. Because you notice as lambda gets smaller and smaller, it's a squared function, the gain seems to apparently fall off, but here's the deal. As lambda gets smaller and smaller for a given length antenna, those gains get bigger and bigger. So it's a trade-off. It may not be that easy. What I'm really trying to tell you is don't get comfortable in thinking, well, I'll just, turn down the frequency and all of a sudden I'll have more received power because this wavelength will go up. Y'all follow me? That doesn't work that way.
You said as lambda gets smaller, the gain gets
Well,
bigger?
lambda is what? Sealed ref. It's inversely proportional to frequency. So if I turn down the frequency, I'd make lambda longer, right? But as I make lambda longer, that half-wave dipole becomes a short dipole. But in other words, the antenna itself changes its electrical appearance to me, and these gains go down too. So you just don't fall into that trap. Right? That's the general formula for any antenna for received power to transmitted power. There's a few things that are not, we're going to do one on this, are not said directly in here, and we'll get to them. I just want to mention this. There's another factor that comes in here, and just put this in now. It's called EP, and that's called a polarization mismatch. And EP is really a cosine squared of what are called the tilt angles. And I'm just going to explain it this way. This is not hard for you to get. If you have an antenna that's vertical, why don't you write that down? It's in the book, and I'll spend a little more time on it, but I want you to just appreciate this. Suppose I have an antenna, it's vertical like this, and I have another antenna. and I'm gonna put that antenna some distance away. Now just look at this. You see how they're aligned? The tilt angle can be measured from any axis, preferably the z-axis. This has got a tilt angle of 0. This has got a tilt angle of 0. The cosine, this is cosine squared by the way. The cosine of 0 is 1, right? 1 squared is still 1, therefore this is 1, no problem, doesn't affect it. Just listen to me now. But what happens when I do this? All of a sudden, the electric field from this one's coming off in this direction, and it's striking this antenna, trying to drive currents vertically, but they're driven this way. Y'all follow me? Well, this may have a cosine, this may be 45 degrees, and this may be 90, or 0 degrees, all right? And therefore, its cosine of 45 is 1 over square root of 2. Square that, we get 1/2. We only get half the power. Y'all follow me? Now, what happens when it does this? Well, the electric field that's launched from this one is trying to drive currents vertically. There's no current that can be driven vertically. It's an antenna that's perpendicular. So therefore, this would have an angle of 0 measured from the z-axis, right? Like this, think of it, opening up. This would have an angle of what? 90, right? The cosine of 90 is 0. Square that, still 0, you get 0 power. That's the basis of polarization mismatch. Just let me do one more thing and you can go. All right, y'all appreciate that? And here's the other kind of mismatch, or other problem. But this is taken care of with the directivity. If I have two antennas like this, y'all see that they're aligned for maximum power transfer, right? But what happens if I do this? Well, now that R vector is no longer perpendicular to this axis, right? It's what? It's at an angle, some theta that is not 90 degrees. It affects the gain of the transmitter. This one also has a theta that's not 90 degrees. It's something else, right? And that's where these gains will change. If you have a mismatch in this, what I'm trying to do is show you like this. If they're aligned for no polarization mismatch, but there's a tilt this way or this way, that is affecting the gain of those antennas or directivity. Y'all follow me? If it's doing this, and you could do it this way if you can all appreciate this. If it's tilting like this, that's polarization mismatch. Got me on that, class? It's important you do. And by the way, in the real world, most of the time when you send signals like from your Wi-Fi, from these Wi-Fi towers, they're bouncing around, they're coming in at all angles, right? There is no such thing as perfect polarization match. You don't have to worry about it. But if you're in the middle of the ocean or out there in the Gulf and you're trying to transmit or communicate with somebody and you got vertical polarization coming at you and your antenna gets tilted like this, you don't get nothing. Y'all follow me on that? All right, if you're close into, if you're in an area like a building where the thing's ricocheting off everything, you'll get some of that signal. But remember this, the further away you are, especially in an atmosphere where the signal can come at you in only one direction, the more you have to be aware of polarization mismatch. Just remember that, because I've never been out to sea and had that happen to me. But you know what an HF whip antennas are? Anybody out here nautical at all? Get out to sea? You got ship-to-shore communication? They're vertical, right? Well, there's always that bright guy that says, that thing's in the way. I just bend it and put it down parallel to the water. That way I won't have problems with the bridge and stuff. And kaput. You can't talk.